Hi everyone. In the last lecture of the surface chemistry, we have discussed the adsorption isotherm. So friends, all of you know that when we consider the adsorption isotherm, there are two types of the adsorption isotherm. Number one is Freundlich adsorption isotherm and number two is the Langmuir adsorption isotherm. So here Freundlich adsorption isotherm, it gives the relationship between amount of substance adsorbed, that is the extent of adsorption, with concentration or pressure at constant temperature. So by using the Freundlich adsorption isotherm, in the Freundlich adsorption isotherm, K and N are the empirical constant, and here the value of the K and N are calculated by using the Freundlich adsorption isotherm. In today's lecture, we are going to consider or we are going to discuss Langmuir adsorption isotherm. So here the Langmuir adsorption isotherm, it gives the relation between the amount of gas adsorbed per gram of the adsorbent and the pressure of the gas at constant temperature. So friends, let us consider the Langmuir adsorption isotherm. So here the Langmuir adsorption isotherm, it based on the various assumptions. So here the basic theory of the adsorption of gases on solid is due to the Irving Langmuir in 1916. He derived the adsorption isotherm in 1916, and here the basic assumptions of the Langmuir adsorption isotherms are: so the first one is the surface of the solid is made up of elementary spaces and each space could adsorb one gas molecule. So here the various elementary spaces are available on the surface of the solid. So here each space, it adsorb one gas molecule. So this is the first assumptions of the Langmuir adsorption isotherm. The second one is all the elementary spaces are identical in their affinity for the gas molecule. Thus the solid surface has uniform adsorption property. This is very important. When we consider the elementary spaces, so here these elementary spaces on the solid surface has uniform adsorption property. Then third one is the presence of gas molecule on given space does not affect the properties of the neighboring space. This is the third one. Then the fourth and very important, due to the thermal energy possessed by the molecules, a few of the adsorbed molecule are detached and pass back into the gas phase, and this is called as the desorption. So all of you know that desorption is the reverse of the adsorption. So here because of the thermal energy possessed by the molecule, so here the few of the adsorbed molecule are detached, that means their desorption will be takes place, that means they pass back into the gas phase. Therefore the adsorption process can be considered or assumed as consisting of the two opposing action. So there are two opposing action. The first one is the condensation and second one is the evaporation or the desorption. So here condensation of the molecule from the gas phase on the surface of the adsorbent, that is a collection of the gas molecule on the surface of the adsorbent, it is called as the condensation, and second one is the evaporation or the desorption of molecule from the surface back into the gas. So this is number 4. Then at equilibrium, the rate of the condensation of molecule is equal to the rate of the evaporation. So here when there is equilibrium, at that time the rate of the evaporation is equal to the rate of the condensation. And here the last one is the adsorbed molecules are dissociated. So adsorbed molecules are dissociated on the surface of the adsorbent. So here on the basis of the assumptions or the postulate, Langmuir derived the following adsorption isotherm, that is the Langmuir adsorption isotherm. So let us consider this diagram. So here this is the adsorbent. It is a 1 square centimeter. So this length is 1 centimeter. This is also 1 centimeter. So 1 square centimeter. So this is the adsorbent. This fraction, this is the occupied fraction theta. So occupied fraction by the adsorbate on the surface of the adsorbent. So here it is denoted by symbol theta. Then here the unoccupied fraction, it is 1 minus theta. So these are the two important terms, theta and 1 minus theta. What is by theta? Theta is the occupied fraction of the adsorbent by the adsorbate, and here the 1 minus theta, it is the unoccupied fraction. That means here 1 minus theta surface is free, or it is a bare, or it is available for the adsorption. So here the Langmuir adsorption isotherm illustration. So once again, theta be the occupied fraction on the total surface covered by the adsorbed molecule. Hence the fraction of the surface available, that is the unoccupied fraction, that is 1 minus theta. So here 1 minus theta surface will be bare, or it is a free. So here the theta and the 1 minus theta. Since the adsorbed layer is unimolecular thick, it follows that only those molecules striking the bare surface can be adsorbed. Number 2, according to the kinetic theory of gas, at constant temperature, the rate at which molecules strike the area of the surface is proportional to P. So this is very important. Rate at which molecules strike the area of the surface is proportional to pressure P. Hence, the rate of the condensation of molecule is directly proportional to the surface available for the adsorption. So here we can write the rate of the condensation. So the rate of the condensation is directly proportional to P in bracket 1 minus theta. P is the pressure and 1 minus theta, it is the surface available for the adsorption. So here the rate of the, from this equation we can write the rate of the condensation is equal to K1 P 1 minus theta, where K1 is the proportionality constant, and this is the equation number 1. Now let the theta be the occupied fraction. So here rate of evaporation, it is directly proportional to theta, because here theta be the occupied fraction, and here, so that here we can say that rate of the evaporation is directly proportional to theta. So here rate of the evaporation is equal to K2 into theta. Again K2 is the proportionality constant, and this is the equation number 2. So here all of you know that as per assumption, or as per postulate of the Langmuir adsorption isotherm, so here at equilibrium, or at adsorption equilibrium, the rate of the condensation is equal to the rate of the evaporation. So we have the equation 1 and equation 2. So here rate of the condensation K1 into P in bracket 1 minus theta is equal to K2 into theta. So here on solving this we can write K1 into P minus K1 into P theta is equal to K2 into theta. So the rearrangement, K1 into P is equal to K2 into theta plus K1 into P into theta. So here K1 into P is equal to K2 plus K1 into P, bracket complete, into theta. Theta is taken as the common, and from this here we can write that theta is equal to K1 into P divided by K2 plus K1 into P. This is the equation number 3. So here multiplying by 1 upon K2 at the numerator and the denominator of the right hand side of the equation 3. So here the right hand side of the equation 3, it can be multiplied by to the numerator and denominator by 1 upon K2. So here equation 3 can be written as theta is equal to K1 by K2 into P divided by 1 plus K1 by K2 into P. So here consider this K1 by K2, it is equal to B. B is the constant. So here this equation can be written as theta is equal to BP divided by 1 plus BP. This is the equation number 4. So here the amount of the gas adsorbed per unit mass of the adsorbent, it is equal to Y, or it is equal to X by M. It must be proportional to the fraction of the surface cover, that is the theta. This is also important. The amount of the gas adsorbed per unit mass of the adsorbent, all of you know that it is X by M. So X by M is equal to Y, and it is a proportional to the fraction of the surface covered, that is the theta. So here Y is equal to X by M, it is directly proportional to theta. So here the Y is equal to K into theta. What is the value of Y? Y is equal to X by M. So here Y is equal to X by M, it is directly proportional to theta. So Y is equal to K into theta. This is the equation number 5. So here we have the equation 4. Equation 4 is the value of the theta. What is the next step? We have to substitute the value of the theta in this equation, that is Y is equal to K into theta. So friends, keep in mind what is the Y? Y is the amount of gas adsorbed per unit mass of the adsorbent, and it is equal to X by M. So here the Y is equal to K into theta. So substituting the value of the theta. So this equation 5 can be written as y is equal to k. So Bp divided by 1 plus Bp. So here the k is constant, b is also constant. So kb is the another constant and it is equal to a. So here this equation can be written as y is equal to x upon m is equal to k into b is equal to a. So here ap divided by 1 plus bp. This is the equation number 6. So friends, this equation 6 is known as the Langmuir adsorption isotherm. So it gives the relation between amount of gas adsorbed per gram of the adsorbent and the pressure of the gas at constant temperature. So equation 6 is very important. So here the constant a and b in the equation 6, a is constant, b is also constant. So here the constant a and b are characteristics of the system under consideration and are determined from the experimental data. So from the, if we have the experimental data, from the experimental data we can determine the value of the constant a and b. So here the validity of the adsorption isotherm is tested as follow. So here we have the equation 6. So that is a y is equal to x by m is equal to a into p divided by 1 plus bp. So by solving the equation 6, here we can write y in bracket 1 plus bp is equal to a into p. So here y into in bracket 1 plus bp is equal to a into p. So here this equation can be rearranged. 1 plus bp is equal to a into p divided by y. So multiply by on the 1 by a on both sides. So here this equation can be written as, that is a p divided by y is equal to 1 upon a plus b upon a into p. This is the equation number 7. So here this equation 7 is the equation of the straight line, or the form of the equation of the straight line, that is y is equal to mx plus c. Here the value of the y is equal to p upon y, that is a p upon x by m. Then here the c is equal to 1 upon a, c is the intercept, its value is 1 upon a. Then m is equal to b upon a, and here the x is equal to p. So here let us plot the graph of y versus x. The value of the y is p upon y and the value of the x is p. So here since a and b are constant, that's why here the graph of p upon y against p is a straight line. And here the slope is equal to b upon a, and the intercept it is equal to 1 upon a. So here this is the nature of the graph, p upon y versus p. So slope is equal to b upon a. Once again a and b are the constant. So here this is the intercept, and intercept is equal to 1 upon a. So here by substituting the value of the intercept, we can find out the value of the a here. So when we plot the graph of p upon y versus p, so just substitute the value of the intercept. So here we will get the value of the a. Then here this is the nature of the graph straight line, determine the slope of the line. Already we have the value of the a from the intercept. Substitute the value of the slope here, a here, we can calculate the value of the b. So a and b are the constant. So here the Langmuir adsorption isotherm, that is equation 6, may be simplified under the limiting condition of the pressure as follows. So here at very low pressure, so there are 3 conditions. So the condition number 1 is at very low pressure, only small fraction of the surface is covered with the molecule. It is therefore possible to neglect Bp in comparison with 1 in the denominator of the equation 6. This is the equation 6. So here at very low pressure, only small fraction of the surface is covered with the molecule. So here therefore it is possible to neglect this Bp as compared to the 1. So here this equation can be written as, that is a x by m is equal to a into p. So once again, all of you know that a is the constant, and from this we can write x by m is directly proportional to p. So here at very low pressure, the amount of the gas adsorbed is directly proportional to the equilibrium pressure of the gas. So here the amount of the gas adsorbed per unit mass of the adsorbent, it is directly proportional to the equilibrium pressure of the gas at a very low pressure. This is the first condition. Second one is at very high pressure. At very high pressure, the surface is completely covered with the single layer of the gas molecule. It is therefore, it is possible to neglect 1 in comparison with the Bp in the denominator in the equation 6. So here this is the equation 6. So here in this equation at very high pressure, the Bp is neglected here, or not Bp, here the 1 is neglected in comparison with the Bp, and here this equation can be written as, that is the x by m is equal to A into P divided by B into P. This PP is cancel, and here X by M is equal to A divided by E. Once again, A and B are the constant. That's why this ratio is constant. So here we can say that this at high pressure, a limiting value of X by M is reached, or the limiting value of the X by M is obtained. This is the second condition at very high pressure. Then here third condition from A and B, that there are two cases at a low pressure as well as at high pressure. So here from A and B, the special case of the Langmuir isotherm can be summarized as, so X by M is equal to constant into P at low pressure. At high pressure, X by M is equal to constant. So here therefore at intermediate pressure, the expression is X by M is equal to constant into P raised to 1 upon N. So here this is the equation at intermediate pressure, where 1 upon N it is lies between 0 and 1. So once again we know that N is the empirical constant in case of the Freundlich adsorption isotherm. So 1 upon N it lies between 0 and 1. This equation is nothing but the Freundlich adsorption isotherm. So here thus Freundlich adsorption isotherm is a special case of Langmuir adsorption isotherm applicable over limited range of the pressure. So friends, this is about the Langmuir adsorption isotherm. So in this lecture we have discussed the Langmuir adsorption isotherm. Thank you.